Okay, let's unpack this. Imagine having a shortcut, like a direct line to understanding the fundamental elemental makeup of absolutely everything around us.
Yeah.
We're talking about peering into this unseen world with just, well, astonishing precision, from the tiniest biological tissue samples all the way up to, massive geological formations.
It's quite a range.
Exactly. And today, we're not just looking at some new gadget. We're doing a real deep dive into a piece of technology that promises to, well, accelerate discovery
Hmm.
and maybe fundamentally reshape how we analyze material science, critical minerals, even our own biology.
Hmm.
This is the Atlas Apex MicroXRF from IXRF Systems, and honestly, it feels like it could be a genuine turning point.
I think it truly is. X-ray fluorescence, XRF, that's been a foundational analytical technique for decades, right? A cornerstone in countless labs.
Absolutely. Standard stuff.
But what IXRF Systems has done here with this new generation, the Micro XRF, it really represents a significant leap forward, a big jump in capabilities.
So when they talk about redefining microanalysis, what does that actually mean in practice?
Well, it's not just about observing more detail, though that's part of it. It's about seeing it faster, yes, but also with far greater sensitivity. And maybe most crucially, extracting smarter, more actionable insights from the data.
Actionable insights, right?
The real goal here, I think, is to kind of democratize sophisticated elemental analysis. Make this incredibly complex data more approachable, more usable, really valuable for researchers across a whole bunch of different fields.
So moving beyond just raw data to actual understanding.
Precisely, and doing it much more efficiently than before.
Okay, and that brings us right to the core of it. The Atlas Apex M and the Atlas Apex X MicroXRF spectrometer, IXRF systems, they've got, what, over 2 decades of experience in XRF innovation.
That's right, solid track record.
And they're unveiling these new instruments, claiming that they'll set a new benchmark for resolution, sensitivity, and automation. Now, that's a pretty bold statement in this field.
It is bold.
So what specifically makes these instruments, revolutionary? Why is it a paradigm shift and not just another upgrade?
Well, the breakthroughs are quite specific, and they seem really impactful. They're designed to tackle some long-standing headaches in microanalysis.
Okay.
Let's start with something pretty fundamental to the workflow. This quick disconnect source mounting. They call it QDS.
QDS, okay. What's the deal with that?
So think about a researcher. They might need super fine detail for one sample, right? Really zoom in. But then for the next, maybe larger sample, they need maximum throughput, speed.
Different priorities.
Exactly. And switching between those often means significant downtime. You've got to realign things, maybe swap out components, recalibrate. It eats up time.
Yeah, that can be a real bottleneck.
Right. But with QDS, they can apparently rapidly exchange the primary X-ray sources. We're talking about going from, say, high-resolution 5-micrometer optics for those tiny details.
5 micrometers, wow.
To high-flux sources, maybe up to 40 micrometers, for speed. And they claim you can do this swap without losing alignment or needing extensive recalibration.
So less downtime, more flexibility.
It's more than just convenience, though. It's about removing those workflow bottlenecks that can really stifle iterative research. The try something, see the result, adjust quickly cycle.
So you can fail fast, as they say. Adapt your approach on the fly.
That's the idea. It accelerates that whole experimental cycle in a way that just wasn't very practical before.
Okay, so QDS definitely sounds like it boosts lab efficiency, lets researchers pivot much faster. But is speed the only frontier here? Or are we also seeing a fundamental change in the quality or the detail of what you can actually see?
Oh, absolutely. It's definitely about quality and detail, too. QDS supports that because it lets you optimize the setup for the best data for that specific task, not just any data quickly.
Right. Choose the right tool for the job, easily.
Exactly. And that leads us directly into the next big thing, unmatched sensitivity.
Sensitivity. How sensitive are we talking?
Well, the Atlas Apex can be fitted with up to 4 silicon drift detectors. These are state-of-the-art sensors, really engineered for incredibly fast, high-resolution X-ray detection.
4 of them.
4, yeah. Totaling a massive 260 square millimeters of active area. By combining 4, they're basically supercharging the system's ability to catch those X-rays.
Like giving it much bigger eyes.
Kind of like 4 pairs of super sensitive silicon eyes, exactly. And each pair is designed to capture X-rays incredibly quickly.
Okay, so what does that translate to in practical terms? More detectors, bigger area.
It means significantly higher count rates. You're just collecting more signal, faster, which translates directly to much faster mapping times.
Makes sense.
And critically, lower detection limits. This is huge.
Lower detection limits.
Yeah.
So finding things that were harder to spot before, trace amounts.
Precisely. Finding even tiny trace elements much more easily. This isn't just about finding more, it's pushing the boundaries of elemental detection down to concentrations that, honestly, you might have previously needed a massive, expensive synchrotron to see reliably.
Whoa, okay. That's a huge claim, rivaling synchrotron data from a lab instrument. For our listeners who might know about synchrotrons, what does that really mean for, say, accessibility, cost, throughput for a regular lab?
It's a massive shift, but I'd say it's complementary. Synchrotrons will always have their place, for certain really extreme experiments needing incredible X-ray brilliance or very specific energies.
The really niche stuff.
Right. But for a huge range of high-resolution, high-sensitivity elemental mapping tasks, the Atlas Apex seems to be offering comparable data quality without needing beam time proposals, travel, all the costs and complexities of a synchrotron facility.
So it brings that power into the local lab.
Exactly. It empowers individual labs to do that advanced research locally, day in, day out, dramatically increases throughput, makes cutting-edge analysis much more accessible.
Okay. So with that sensitivity, we can find these trace elements, but just knowing there isn't always enough, right? You need to know where they are. Precisely.
Spot on. And that brings us to the high-resolution mapping capabilities. The Atlas Apex uses something called true perpendicular beam geometry.
True perpendicular.
Yeah, and optics that can get down to that 5-micrometer spot size we mentioned.
Okay, true perpendicular beam geometry. That sounds very specific. What makes it true, and why is that important? Does it prevent distortion or something?
That's an excellent question. It's a critical detail. Imagine trying to map a complex surface, but your X-ray beam is coming in at an angle. It can create sort of perspective issues, shadows, warping your view.
Like trying to read a map tilted sideways?
Kind of. True perpendicular beam geometry is like shining that X-ray beam perfectly straight down 90 degrees to the sample surface. This design essentially eliminates those geometric distortions and optical artifacts.
Oh.
It ensures that your 5-micrometer resolution isn't just about seeing tiny features, but seeing them exactly where they are in relation to everything else. Spatially accurate, distortion-free mapping.
So it avoids misinterpretations you might get with older, maybe off-axis designs.
Precisely. Especially in complex, maybe uneven or three-dimensional microstructures, it just removes that ambiguity, gives you much clearer, more reliable spatial information.
Clarity, right. Okay, speaking of challenges, what about those notoriously tricky lighter elements? Things like carbon, oxygen, nitrogen. Are they still a bottleneck?
That's a fantastic point. Detecting those light elements accurately with XRF has always been challenging. The X-rays they emit are lower energy, easily absorbed by air.
But they're so important. Carbon, oxygen, the basis of organic chemistry biology.
Absolutely fundamental. And critical in advanced materials, too. Polymers, composites. Well, this is where the enhanced vacuum capability comes in. The Atlas Apex can operate under a pretty high vacuum, below 0.1 kilopascals.
Okay, so pumping out most of the air.
Exactly. By minimizing that atmospheric interference, specifically the absorption by air molecules, it allows for much clearer, more reliable analysis of these previously difficult elements, specifically from carbon upwards on the periodic table.
So a real breakthrough for carbon detection.
It seems like a really significant step. This isn't just a minor tweak. It genuinely unlocks new possibilities in biology, environmental science, materials development. Think about mapping carbon distribution in new battery materials or oxygen within a cell. Without super complex sample prep, it's potentially huge.
That sounds incredibly empowering for those fields. Now, one more practical thing. Researchers often deal with wildly different sample sizes, right? From tiny specks to quite large chunks. Does this system handle that variability?
It certainly seems to address that constraint head-on, which is a major practical advantage. This leads us to its largest sample capacity in its class.
How large are we talking?
The specs say it can analyze specimens up to 7 kilograms. That's quite substantial, over 15 pounds.
Them kilos. That's a serious chunk of rock. Or maybe a decent-sized manufactured part.
Exactly. And the matting areas are pretty generous, too. The M model is 220 by 200 millimeters, and the X model goes up to 400 by 300 millimeters.
Wow. So you might not need to cut up that valuable fossil or dismantle a complex part just to analyze a small section?
That's the implication, that ability to analyze larger, intact samples non-destructively.
Yeah.
It doesn't just save time and effort. It can fundamentally change the scope and integrity of a study. You're looking at the whole picture.
Okay, so we've got this really impressive hardware. The quick change sources, the super sensitive detectors, the perpendicular beam, the vacuum, the big sample stage. But even the best hardware needs smart software to run it.
Right? You got it. The hardware is the muscle, but the software is the brain. And IXRF is highlighting Iridium Ultra, which they call their most advanced software platform to date.
Iridium Ultra. So how does this software make all that powerful analysis more accessible, more insightful, especially for users who maybe aren't XRF gurus?
That seems to be a key focus. Bridging that gap between complex instrumentation and getting actionable results easily. For instance, they talk about an AI-assisted workflow.
AI-assisted, what does that involve?
It sounds like it provides contextual guidance, maybe recommends optimal settings based on the sample type or the goal, and offers real-time insights into the data as it's being collected.
So it kind of holds your hand through the process.
A bit, yeah. It streamlines the operation, making it easier for users with varying levels of expertise to get good, accurate results without getting totally lost in tweaking dozens of parameters. It lets them focus more on the science questions.
That sounds like a huge plus, especially for labs with multiple users or for researchers trying new types of analysis.
Yeah.
What about specific tasks? Does the software have built-in smarts for those?
Definitely. Mineral classification is a great example they highlight. The software apparently has automated routines for identifying and mapping common minerals.
Oh, wow. So it could look at a geological sample and automatically flag areas of, say, calcite, or what were those rare earth minerals? Bastnasite.
Exactly, basmasite, parasite. It could potentially identify and map those phases automatically, which would save geoscientists and material scientists just countless hours of painstaking manual interpretation.
That's powerful. But what if you're looking for something really specific, some unique relationship between elements that isn't a standard mineral?
Yeah, good question. That's where customization becomes key. And they have something called the custom map calculator.
Custom map calculator. Sounds intriguing.
It seems to offer really unparalleled customization in how you visualize the data. Users can apparently build their own elemental maps based on user-defined formulas or ratios between elements or other mathematical expressions.
Ah, so if your hypothesis involves, say, the ratio of iron to manganese being important, you could create a map that specifically shows that ratio across the sample.
Precisely. It lets you create visualizations tailored to your specific research question, highlighting subtle relationships that standard maps might obscure. Really powerful for testing specific hypotheses.
That ability to create custom views sounds incredibly useful for pushing the envelope. But one common challenge in XRF is accuracy, right? Especially when elements have overlapping spectral peaks. It can be hard to tell them apart.
Absolutely. That's a classic problem, especially in complex samples. You get spectral interferences where the X-ray signals from different elements are just too close together. It's like trying to distinguish two instruments playing almost the same note.
Right. How does Iridium Ultra handle that?
This is where live spectral deconvolution comes in, and it sounds really important. Think of it as a sophisticated real-time filter.
Yeah.
As the data is coming in, the software is actively working to separate those overlapping peaks, mathematically untangling the mixed signals to figure out how much of each element is truly present.
It does this live during the scan.
That's what live suggests, yeah, which is crucial for achieving confident, accurate identification and quantification, even in really messy, complex samples where elements are trying to hide behind each other spectrally. It helps turn ambiguous data into trustworthy results.
Confidence in the results. That's key. And finally, just from a practical standpoint, keeping the instrument running smoothly.
Right. Uptime is crucial in any lab. They mention automated diagnostics built into Iridium Ultra.
So the system kind of monitors itself.
Sounds like it. Smart system support designed to potentially identify issues early, maybe flag things for maintenance before they become major problems. Reducing downtime, simplifying troubleshooting keeps researchers focused on research, not repairs. A small feature maybe, but invaluable day to day.
Definitely. Okay, so we have this incredibly powerful hardware driven by intelligent software. Now, let's connect it all to the real world. Where is this technology making a tangible difference right now? You mentioned critical research challenges. Here's where it gets really interesting.
Yeah, this is where you see the impact. And one of the most significant areas is definitely critical minerals. Supporting exploration, understanding resources, sustainable development, these are huge global issues right now.
Absolutely. We hear about critical minerals constantly.
So one example they provided is from the U.S. Geological Survey, the USGS, out in Spokane. They use MicroXRF to map a rare earth element-rich carbonatite dike.
A carbonate, okay. Rich in rare earths.
Exactly. And the map didn't just show, rare earths are here. It beautifully revealed the distribution of specific minerals. Calcite, altered barite, and importantly, specific Re-bearing carbonates like bastnasite and parasite.
So it identified the exact mineral hosts for the rare earths.
Yes, but even more than that. What's really fascinating is it highlighted zoning within individual crystals, variations in calcium and neodymium content across a single crystal.
Wow, that granular, down to zoning within a crystal.
Yeah, and that level of detail is vital for understanding how these rare earth elements got concentrated there in the first place, the mineralization process. It helps with dating the rocks, understanding the whole geologic evolution of these deposits.
Which is crucial if you want to find more of them or extract them efficiently.
Exactly, especially for those critical RAEs like lanthanum, cerium, neodymium, the ones essential for magnets and EVs, wind turbines, defense tech, you name it.
Incredible detail, and that level of precision must really help target exploration and make mining potentially more sustainable.
That's the goal. Identify richer zones earlier, understand the concentration mechanisms better. Another quick geology example, the analysis of Memphis nodules.
Memphis nodules, like manganese nodules.
Sort of. These were soil ferromanganese nodules. The MicroXRF mapped how iron, manganese, and also the rare earth element cerium were enriched in these nodules. It showed really clearly how geological and soil processes, specifically redox reactions, can concentrate these critical minerals.
So understanding natural concentration processes.
Precisely. This kind of high-res elemental mapping is key to figuring out how and where these valuable resources form and accumulate in the crust and soils.
Okay, so that's the earth sciences. Moving from rocks to, well, us. You mentioned neurodegenerative research. How does this help unravel brain diseases, especially linking back to that synchrotron rivaling claim?
Right. In neuroscience, trace metals, iron, zinc, copper play critical roles, but their dysregulation is implicated in diseases like Alzheimer's and Parkinson's.
Okay.
The Atlas Apex allows researchers to map these trace metals in brain tissue with extraordinary spatial detail. There's an example from the Tanagawa lab at MIT's Pekauer Institute.
MIT.
They produced a high-resolution MicroXRF map showing iron and zinc distribution in mouse brain tissue, and the quality, the detail, it really does approach what you might get from a synchrotron, but again, on a lab-based instrument.
Making that level of research much more accessible.
Exactly. It offers incredibly precise insights into how trace metal regulation might be linked to cognition, memory, and disease progression. The potential impact is huge. More labs can investigate these links, potentially finding new diagnostic markers or therapeutic targets much faster without the logistical hurdles of synchrotron access.
That really does sound like it democratizing that cutting edge of research. So beyond critical minerals and brain research, where else is this technology pushing boundaries?
It's making waves across several other vital areas. Think about advanced materials and batteries.
Energy storage. Big topic.
Huge. The Atlas Apex lets engineers precisely map, say, lithium distribution in new battery electrode designs, or track how materials degrade at the micro level. That drives breakthroughs in battery life, capacity, safety.
Powering the future, literally.
Right. Then there's phytometallomics, basically, studying metals in plants.
Okay. Why is that important?
It helps us understand how plants take up essential nutrients, but also how they might absorb toxic metals from contaminated soil. This has big implications for improving crop yields, food safety, and even using plants for environmental cleanup phytoremediation.
Fascinating. And you also mentioned semiconductors and microelectronics.
Yeah. In that world, purity is everything. Even a few stray atoms of the wrong element can kill a microchip. The ultra-sensitive, high-resolution analysis is crucial for quality control, failure analysis, and developing the next generation of smaller, faster, more powerful devices.
Makes sense. Purity is paramount there. And even in fields like paleontology, you said, looking at fossils.
Absolutely. There was a great example mapping a sea cucumber fossil from the Mason Creek Lagerstätte in Illinois, famous for amazing fossil preservation.
A fossil sea cucumber, okay.
Yeah, done with Professor Roy Plotnick. The elemental map revealed the distribution of calcium, iron, sulfur even trace amounts of arsenic.
Arsenic.
Interesting. Yeah, and this provided completely new insight into fossil preservation. How did these soft-bodied animals get preserved so well in these ironstone concretions? It also sheds light on mineral cycling and rare earth geochemistry in these ancient environments.
So the elements tell a story about preservation itself.
Exactly. It's like reading the chemical history of the fossil and its surroundings. It shows how versatile this elemental mapping is, bringing clarity to complex questions across basically every scientific discipline you can think of.
It really does seem to circle back to that quote from the IXRF CEO, Bill Williams. He said the Atlas Apex combines precision-engineered hardware, high-throughput detectors, and smart automation.
To give researchers more flexibility, speed, and confidence in their results than ever before.
Yeah, it really captures it. And it embodies their tagline, too, bringing clarity to complexity, making that microscopic elemental world undeniably clear, accessible, and ultimately actionable.
Well put.
Well, what an incredible exploration this has been. We've seen how these huge capabilities of the Atlas Apex MicroXRF aren't just about a fancy new instrument. It really feels like a pathway to genuinely unprecedented insights across so many areas of science and industry. This deep dive, I hope it's shown you how one piece of technology can really ripple outwards, impacting everything from understanding our planet's vital resources to perhaps, eventually, unraveling the deepest mysteries of the human brain.
It makes you think, doesn't it? If this technology lets us see the fundamental elemental building blocks of our world with such, well, unprecedented clarity and precision, what new frontiers are we going to unlock? Especially about how things are connected.
Also,
Well, consider this. If you can truly understand the detailed elemental story of a single rock, or a plant, or even just one brain cell, how might that fundamentally change our perception of the larger systems they belong to? We might start seeing patterns, interconnections that we've never even considered before.
seeing the big picture by understanding the smallest parts.
Exactly. The possibilities, as we keep refining our ability to see the invisible elemental world, they feel truly boundless.
A fascinating thought to end on. Thank you for joining us on this journey into the Atlas Apex MicroXRF. If you're as compelled by these advancements as we are, you can definitely learn more by visiting www.ixrfsystems.com.